and welcome to class 6 of the Optimization Masterclass. We are almost halfway through the course because we are planning to have 12 videos. If you want to check again what are the topics of the videos, you have a video in the channel. And you have there all the topics by class. They can change slightly, but we want to cover them, but maybe the order is not the same as you see it there. So what are we going to talk about today? We are going to complicate even further the model. So we will add transfers. So transfers are like in the SAP terminology STRs and STOs. Purchases, so when you buy something externally to your company, either raw materials or even finished products, then we would model target, safety stock, max stock. So this is kind of the same concept. We will just show you one and then the rest follow. And storage constraints. And at the end, we are going to talk about the restrict table, which is a very good tool for increasing the performance of your models. But you can use it with other purposes, and we will tell you exactly for which purposes. The homework, here I put on the slides the correct way to write the constraints about the production hours and the production capacity. But Felipe is going to switch to the app to show you how to write those constraints in the app. And you have them here as well.
Is the app for homework 2. And here I'm already showing the complete model. And the exercises are essentially this one here, the production rate and the resource capacity. In this case, I'm not including the shelf life since that was a very complicated exercise. And I'm going to show how will you solve this exercise in the app. So you cannot be showing the full model. And here we have the additional sets, variables, and parameters that are needed and that are going to be used into the constraint implemented in the exercise for both production and production hours and resource capacity. Then when you come down here, you pick the exercise that you want to solve and production rate constraint. Production rate constraint is how much you are producing. So the production is equal to the sum across all resources of production hours times production rate. And that's it, the exercise.
When you press enter, did you notice there is a running man above? So then the model is running instantly, basically.
Yeah. And when it runs, even though it passed the syntax check, it might still be wrong. So you need to then look at the reports and confirm that everything makes sense. And yes, this is production hours and resource capacity, also another simple exercise. So the sum over product locations of production hours less than equal than available capacity. So you have these ints down here, and then you just need to pick the different pieces and put them together into the constraint. And then you go to the reports and you confirm if everything is correct. Yeah, and that was the homework 2.
Okay, thank you, Felipe. Let me share back the screen. And let's get started with transfers. So as I said, transfers, I'm using this word, let's say generic word, but in the SAP terminology, this is like STRs, so stock transfers request. And you also have this notion of STOs. So STOs are like confirmed transfers. So those are usually coming into a solver as an input. So they are fixed. So somebody confirmed them in SAP, and then you integrate them into your tool. But then you also want the solver to see if you have further space to move stock across your locations. So those are transfers in and transfers out. And here their dimensionality is by product, from location to location, and period, all of them. And basically, the only thing you need to do is to add them in the material balance, but there is a little twist because you need to sum them. So, because material balance is by product location, but here we have product from location to location, so you have two locations. So you need to restrict the dimensionality, which means you need to sum on one of the dimensions. So for transfers in, we sum on the from location. I will explain in a minute why. And then transfers out, they are with minus, right? Because they are out of the location. And you sum by the to location. And here I'm explaining a little bit that I'm using different words. In the model that we are using in the app, we have this from location to location, but how can we say them differently? So you have source and destination, right? Oops, sorry. So then, I have a problem here. So then transfers in, right? Source and destination. If you are a location which receives a transfers in, it means you are the destination, right? And the source is all the other locations in the network. So this means you need to sum by the source. So you are the destination. So you write the constraint on the destination and you sum all the other quantities coming from the other sources, let's say in the network. And then the transfers out is the other way. So transfers out, it means you are the source. So if you transfer out from one location, it means that that location is the source. So you need to write the constraint for each source, but you need to sum by destination, meaning that you source to multiple destinations. But the constraint, you write it on the source, right? Because that's you are the source of the transfer, you are the source of the materials, and then you source it to various destinations. And as I said, you need to do that so you can fit it in here in this equation, the material flow equation. So this is just a little bit you need to practice it, and an occasion to practice it is also by doing purchases, because the purchases have the same principle, that you have a location in your network and a supplier which is outside the network, but it's basically another location. So you need to sum over either the product or supplier, and I will let you figure it out over which one you need to sum, such that you can add it in the material flow. And then the equation now becomes ending inventory is equal to starting inventory, so what you have at the beginning of the bucket, plus what is being produced, plus what is being supplied from outside your manufacturing facilities. Then transfers in what comes into that location. Also, met demand, it's a minus, we subtract it. Sorry, transfers in are with plus, met demand, and transfers out are with minus because they are leaving basically the node. This is what I explained, I think, in the first lesson. So I will let you figure out how to sum the purchases, and then next time we will check it in the homework. And now let's talk about the other, let's say, big concept we have in this lesson is the target stock. As I said, it's the same principle for target stock, safety stock, max stock. I will just show you how to think when it comes to the target, but the same applies. So basically the same equation. So now that we learned about the slack variables and how to transform a hard constraint into a soft constraint, this is what we are doing here as well. So usually the target stock, it's an input, right? For example, for this product location, my target stock is 50 each month or each bucket. And I want, at the end of the day, the ending inventory to be equal to this target stock. So this would be a hard constraint. If we just write ending inventory, which is a variable, I want it to be hard constraint to be equal to the target stock. But we know that's not possible all the time. So that's why here we use two slack variables. One below target, so a variable which keeps track of how much you can go below target and how much you can go above target. So now to explain this, but I don't know what's happening today. I have something here. Okay. So if the ending inventory is bigger than the target stock, then below target is 0, right? Because if the ending inventory goes above the target stock, you are not below. So the idea is that you cannot be both below and above target. So one of them will be 0. So then the equation becomes target stock equals ending inventory minus above target. If the ending inventory at the end of the day, due to capacity constraints or other constraints, is less than the target stock, then the above target becomes 0, and then the equation is written, or let's say here we only have the non-zero values, right? So that's the idea with those ones. You have two of them, but they cannot both be bigger than 0 in the same time, because you are either below target or above target, but for each product it can be different, or even for each bucket. In one bucket you can be below target, in one bucket you can be above target. So then you need to add those constraints, right? And the dimensionality is very simple because they are all on product location. And just a little recap. So the target stock, as I said, it's an input, or how we call it in AMPL is a parameter. So this comes from the input data. The ending inventory, it's a variable, but the same above and below target. They're also variables, and they vary between buckets, products, locations, and so on. So now, because we use those slack variables and we transform this hard constraint into a soft constraint, we need to put a penalty in the objective function. So this is what I'm showing here. So in the objective function, we still put a lot of pressure on the solver to minimize the unmet demand. This is, let's say, the most important thing. And then we start playing with this below target and above target. Here I wrote an example in which you take below target, the other one with above target, but you can also put both in the same objective function and say, if I'm below target, I pay a penalty of 5. If I'm above target, I pay a penalty of 50. So you can do that. Here I just put them separately. And you also need to put a penalty on transfers in and transfers out in case you have them in the model, because otherwise, if you don't put even this very minimal penalty, then the solver starts to move production through all the network, because if there is no penalty, it says, well, I can transfer this here and then here and here and bring it back. So this is super important to have this penalty. It was a bit like how we had a penalty for the ending inventory. Before we had the targets, we had to put a penalty for the ending inventory. Otherwise, the solver was producing as much as it wanted because there was no penalty to keep the ending inventory 0. And here also, like a little homework, just check, make sure that the dimensions are aligned between all the concepts in the objective function and the objective function itself. So here you need to pay attention. So you might need to sum again, right? Because transfers they have two locations, but the objective function is on product location period. So you also need to sum. So that's a tip for you. And now another nice concept where we are going to see how we can do layered penalties, right? And we chose the storage capacity because it's quite a simple concept. So the storage capacity refers to, so you have a physical location, how many physical products can you store, right? And sometimes this is a very hard constraint. Some companies have very little storage, so you need to control this very well. And in that case, you make it a hard constraint. And you say, well, at the end of the day, ending inventory should be less than in this max location capacity, which is an input, right? Let's say 5,000. I can only store 5,000 products in this facility. So it's summed on the product. So it doesn't matter which product. All the products that I produce, I can only store 5,000 of them in this location. So this is the hard constraint. But sometimes you have some room and you say, well, my max is 5,000, but I don't know, depending of the day, for example, I can make space for 200 more products or 10 products. And then you can use the same Slack variable trick to put a penalty and say, if I have this max capacity, but if I go above with 5 units, then it's bad, but the penalty is 10, let's say. But if I even go above that, the penalty is 50, which is very big. If you remember, it's even bigger than the unmet demand, right? And also here, above capacity. So I pay the same penalty as the unmet demand. So yeah, maybe you need to here pay attention. What's more important, to have unmet demand or to go above this, right? Because if you say, well, I don't have storage, then you lose the demand. So then you need to see how do you play with it. In this case, as we put it, they have the same power, let's say, unmet demand and going above capacity. But you need to think, is it important for me to have unmet demand and lose a customer, or try to find a way to find more capacity? So this is a bit how you're thinking about this. And now Felipe is going to show you how you implement this in the app.
Okay, so here is the app for homework 3. And there are, I'm not showing the complete model, okay. So in terms of exercises here, you have the transfers to implement, you have the target stocks to implement, and I'm going to show storage capacity and solve it. This is also the easiest exercise. So for the storage capacity, we have a parameter with the maximum capacity, and then we need to implement the constraint that is going to ensure that for every location at every time period, we are under the capacity limit. So we come here to the exercises, we pick storage capacity. And so we have this constraint over all locations time periods with some overall products in that location. We take the ending inventory, and that needs to be less than equal to that total than max capacity. Press enter and it is solved. Then you can confirm the results. And this is the version without layers. So
yeah, this is the hard constraint.
Yeah, we have this hard constraint. It needs to be under that max capacity. Now let's imagine that is not so hard. We can go a little over, but with a penalty. So now the layered version. For the layered version, there is another variable that is going to be above capacity slack between 0 and 20. So we can go over that capacity up to 20 units. And in the exercise, it is very similar to what we had before. Sum of ending inventory less than equal than max capacity plus above capacity slack. And that's it. So this part is done. And here we have this slack that we need to penalize in the objective. One way to do this in Ample is just like this. You can, so we have the other components already taking consideration the transfers and the target stocks. And here we have this additional sum overall locations periods. If the above capacity slack is greater than 1, then if it is less than 5, we have a penalty of 10, otherwise 50. And that's it. You just put this in your model, and this is going to automatically turn your model into a MIP. So I can show you here. Now we have binary variables that were created. So on other modeling tools, you will need to be creating the debuggings yourself and creating these additional binary variables. In Ample, you just write the logic and we take care of that for you. And just like I did these for debug capacity, just like we have these other penalties, the same could be done there. So as an exercise, you can also play with this and try to see how would you do layered penalties for above target, below target, and so on. But it's always like this. You can just write logic and have the different values. And another possibility for this type of penalties is also to use piecewise linear functions. That is also something that can be useful in case you want to change the rate of penalty at different points. And that way you also stay as an LP, so easier if you have a very large model. Yeah, and that's it.
Okay, thank you. Yeah, that's super fun, transforming all this hard constraint into soft constraint and doing the penalties. So now, as Felipe said, homework, you can practice with the max stock, right? So let's say max stock, but this is by product location. So the storage capacity was by a facility, by a location. But max stock is by product location. So here I'm just taking an example. So let's say max stock, this is the input, is 100. And then you need to write the constraints, and actually it's more about the penalties. So if ending inventory is between 101 and 119, then the penalty for going above max is 50. And then if you go further, then the penalty for going above this max stock is 5,000. So that's like nearly impossible. This should never happen. And as Felipe showed you, you can very easily implement this in Ample. Otherwise, it gets a bit tricky. But there are ways, as you said, the piecewise functions. And the last concept for today, as I said, the restrict tables. Those are the tables which basically restrict the input into the solver. And this is a very good tool to reduce the size of the model. And the quick example here, it's the product location, and you have this in the app. There is a checkbox, so you can use this restrict or not. And if you don't, what happens? You have products, locations, and then you have the set of combinations of product locations. And the number of elements of this is less than if you have the Cartesian products of product and location. So for example, if you have 50 products and 100 locations, then you have 500 combinations. But maybe you don't have all those combinations, for sure. You don't have them normally. And from the data from the customer, you get that the number of some products you can find only in some locations. So in total, you have 237. So that's half of the combination. So this makes your model in half. And when you have huge models, this is very important because you really help the performance of the models a lot. So sometimes if you don't put those restrict table, the model doesn't even run. But if you restrict all the concepts, like product location, product resource, sorry, also about the transfers, right? From location to location. You don't have all the possible combinations. So you just need to include in the model only the lanes that make sense. And in that case, this helps you increase the performance of the model. Another way in which you can do that is if you want to debug, and for example, you add some constraints, it's super complex, you don't know how to debug it. And then you limit your model. Say, well, I only want to do 5 products. I have 5,000 products, but I don't understand what's happening in this model. So then with this restrict table, you just say, well, I'm just going to run this model for 5 products and 2 locations. And then when you do that, because you already set up this restrict table, you immediately use the very small restrict table and you run the model. And in that way, you see much better what's happening, right? Ideally, you should have one. So you isolate one product or one location, check what's happening. Is the solver still infeasible? Is the constraint still giving weird results? And then you keep adding, right? So this is also a debugging tip. somebody asked me, oh, I have this model, it has all those constraints, I don't know what to do. Reduce the model, maximum 5 products. If you can, just put 2 products. 2 products, 1 location, or 3 products, 2 locations, because this is much easier to see what's happening. So this is very useful. But in which situation is actually good to put all the products and all the locations? You can do that when you have a network design solver, which means that it's kind of this strategic solver. And if you are a distribution company, let's say you buy construction materials and then you need to sell, so you buy them from external suppliers, and then you want to sell them in your shops. And then you need to analyze which products are best kept in which location, right? And then what you do is you create this solver where you leave everything open. You put all the product, all the locations, all the lanes, basically, right? And then you let the solver free to run and you see what's happening. Where does the solver because the solver basically optimize in terms of costs usually, right? What are transportation costs, inventory holding costs, and so on, and demand, of course. So then you have this free version optimized network, right? And then you start analyzing, and maybe you decide, well, actually, this lane doesn't make sense. You start building your restrict table. But what you started with was the complete openness of the network. So this is, let's say, a use case for which when you don't need restrict table, but eventually you do, because as I said, the customers, they just leave all the lanes open and they look and then they say, well, actually, this makes, what if I close this lane? And they start to check the costs and so on. So you still end up with a restrict table. But normally when you have a manufacturing solver, so not a distribution network solver, so manufacturing, for sure you need the restrict tables, because you usually have also other constraints which transform your solver into a MIP, like lot size, campaign planning, and other things. So then making the model as small as possible, it's actually sometimes the only way to be able to run that solver. Okay, here very quickly, some recap. I think I said that in another session, is what is the power of optimization? So the idea is that you put all the decisions are taken in the same time, and you take into account all the constraints and all the data. And then it's not only about the constraints, but also the full horizon. So the solver looks at optimizing everything over the full horizon. So for example, when you put this penalty about the unmet demand, then the solver sometimes pre-builds because it doesn't want to pay the penalty for the unmet demand later in the horizon. So it produces it better. So yes, penalties costs are accumulated over the full horizon, and as we've seen today and the previous lesson, constraints can be soft, like targets, or hard, like capacity, but also targets can be hard and capacity can be soft. And depending the type of the solver, you can have one or the other. And I think this is all for today. Next week, we will check the homework, how I did today, and we will see how can we validate the results, because now we are just showing you the formulation and so on, but when you want to validate results, what do you check? And then another debugging tool is to test with extreme values, right? What if you put one demand 1,000,000 and the rest is 0? See what happens, and so on, because this shows you a lot about the behavior of the solver. And then we will model lot size. So a minimal incremental lot size. And as I said, this transforms the solvers into MIPS. So you start to pay attention to the performance. And scenario functionality. How can you check different scenarios, to compare, to analyze, and so on. This is it from today. As I said, we are halfway through the course. We are also planning to organize a Q&A session, and we will keep you informed of when we will have that. They will be live, and you can watch all the videos and write down the questions that you have. Thank you very much for joining, and we will see you next time. Bye.